I'm Forrest Tanaka, and this is part 2 of my astrophotography series. And this time, I'll be talking about telescope mounts. Now in part 1, I talked about telescope OTAs, so make sure you have a look at that if you still haven't chosen an OTA for your telescope or your astrophotography rig. In this part 2, we're talking about mounts. Now, if you have a mount that's useless at guiding your telescope accurately, you're not getting a good shot no matter what you do. But if you have a great mount and great technique, you can take amazing shots, even with a mediocre OTA. Now, why are mounts such a big deal? Most of the celestial objects you'll photograph are really dim, and things like nebula and galaxies can take really long exposures, hours in some cases. Now, of course, since the Earth rotates, the sky doesn't stand still. And at the focal lengths we're talking about, objects will race across your telescope's field of view.
This is video of Jupiter crossing my Maxidov Cassegrain's 1300mm field of view in real time.
Now you can go back and look at a video I made where I took a photo of the Andromeda Galaxy at 280mm. I couldn't take a photo for longer than a second before I got noticeable star trails. Now this telescope, 900mm focal length. This little Mac Cass is 1300mm. The only astrophotos you're going to take with these, without tracking, are really bright things like the 5 closest planets or the moon. If you're going to take photos of anything else in the sky, you're going to need a motorized tracking mount. This video is all about choosing and using a motorized tracking mount. Now there are two main kinds of mounts for astrophotography: AltAs mounts and Equatorial Mounts, or EQ mounts. Now let's first talk about the AltAs mounts because they're really common and fairly inexpensive. The name AltAs comes from a celestial coordinate system. You need celestial coordinate systems to specify where things are in the sky, and your telescope needs those celestial coordinate systems to be able to track objects across the sky.
Alt is short for altitude, and it's just the number of degrees above the horizon, 0 at the horizon, to 90 degrees at a point directly above you, which is called the zenith. Az is short for azimuth, and it's the fancy word for the compass direction based on geographic north, not magnetic north. 0 degrees directly north of you, 90 degrees due east, 180 degrees due south, and 270 degrees due west. This coordinate system doesn't move relative to you, so as you move around the world, this coordinate system moves with you. Or as you stand still and the Earth rotates, again, this coordinate system moves with you. And stars and planets in the sky pass over this grid that looks stationary to you. That means moment to moment, and even as you're moving, every object's altitude and azimuth changes.
AltAs mounts have two motors. Now one is flat with an axis perpendicular to the ground, and that lets you adjust the telescope's azimuth coordinate. The other motor has an axis parallel to the ground, and that lets you change your telescope's altitude. And together, they let you point at anything in the sky and track anything in the sky. So it's easy to see how an AltAs mount can point at anything in the sky, or slew to something in the sky, to use astronomers' jargon. But how do they track objects as they cross the sky? Now, to think about this, it's easiest to think about the degenerate cases, where you're tracking objects at the North or South Pole, and when you're tracking objects while you're at the equator.
Imagine you're at the South Pole. How do the stars move across the sky? You can see the stars just rotate in circles all around us. To track any object from the South Pole, you really only need the azimuth motor because nothing really changes its altitude during the night. Only its azimuth. Now imagine you're in Quito, Ecuador, which is just barely south of the equator. Now how do things move across the sky? If you follow a constellation like Orion as it rises due east, it passes directly through the zenith and sets due west. In that case, we don't theoretically need an azimuth motor. Only the altitude motor tracks objects going through the zenith. Now, any objects that aren't going through the zenith, we have to track using both the altitude and azimuth motors. Most of us don't live near the equator, and definitely not at the poles, so we get the in-between case. Celestial objects rise in the east, then head south if you're in the northern hemisphere, or north if you're in the southern, and then crosses the meridian. The meridian is an imaginary line from due north to due south, marked with a bright yellow line here. Then heads back north in the northern hemisphere, or south in the southern hemisphere before finally setting in the west. To track objects, the azimuth motor mostly moves at a constant rate through the night, but the altitude motor first moves the telescope up, but gradually slows down as the object reaches the meridian. Then it moves the telescope back down until the object sets. A computer on board AltAs Mounts calculates how it should move the mount depending on where you're pointing it.
So that's pretty easy. As we see objects move across the sky, AltAs Mounts see objects moving across the sky the same way. But AltAs Mounts aren't without some pretty serious problems.
The most obvious one is object rotation. Let's look at Orion. You can see it rise with his arm holding an animal skin first, that looks kind of like a bow. Then in the northern hemisphere, he's standing straight up at the meridian. As time passes, his pelt gradually points downward before setting pelt first. Very clearly you can see as the telescope tracks anything, its image rotates on your camera's sensor.
The second problem is mechanical. Even the finest telescope mounts have a little bit of slop in the gears. Now, as long as the driving gear is always pushing on the driven gear, that's more or less okay. But with an AltAs mount, the altitude motor starts in the east by pushing on one gear. But then as it gets closer to the meridian, it slows down, stops, and then starts pulling on a gear. All that time around the meridian, you're dealing with gear slop. And if you're trying to track objects in the sky accurately, that gear slop makes it pretty hard to do. The second kind of mount is called the Equatorial Mount, or EQ mount for short. They come in a lot of variations, but the most common kind for backyard astronomy is called the German Equatorial Mount, or GEM. And this is one of them. Now, like AltAs mounts, they have two axes of rotation, but instead of azimuth and altitude, they use right ascension and declination. And these terms come from a different and, for astronomy, more useful celestial coordinate system.
Now imagine the Earth is inside a spherical scaffolding made with struts that look like longitude and latitude lines of the Earth. The north and south poles of the Earth point to the north and south poles of the scaffolding, and the equator of the Earth matches the equator of this scaffolding. That imaginary scaffolding is called the equatorial coordinate system. The poles of the scaffolding are called the north and south celestial poles, and the equator of the scaffolding is called the celestial equator. Now, spin the Earth inside, and you have a good model in your head for what you're seeing. The longitude lines of this celestial sphere are called right ascension lines, and like longitude lines on the Earth, they tell you how far east or west things are. The latitude lines are called declination lines, and they tell you how far north and south things are. Declination, usually called dec, are measured in degrees, with 0 at the celestial equator and 90 at the celestial poles, either north or south. But right ascension, usually called RA, while it can be measured in degrees, minutes, and seconds, you'll usually see it in hours, minutes, and seconds. 0 hours goes right through the constellation of Pisces. 90 degrees east of there is called RA 6 hours. All the way on the other side is RA 12 hours, and another 6 hours gives you RA 18 hours. All the way back to RA 23 hours, 59 minutes, 59 seconds, and RA 0. So if an object at RA 6 hours is rising in the east, in another 6 hours on the clock it'll be directly on the meridian, and it'll set in another 6 hours, so it's a really convenient system. The big thing to notice in comparing the equatorial coordinate system with the altitude azimuth coordinate system is that the altitude azimuth are relative to you, and celestial objects slide over the coordinates. The equatorial coordinate system doesn't care where you are. and the coordinates of celestial objects don't change with the equatorial system like they constantly change with the altitude azimuth system. The star Vega is at RA 18 hours 37 minutes 23.51 seconds, and declination 38 degrees 47 minutes 50.2 seconds, regardless of where you are or what time it is. Now, some things do have changing RA and dec, like the moon, which moves a little less than an hour of RA per 24 hours, which makes sense since it has a 28-day orbit, and RA goes from 0 to 23.
Even the stars are changing their RA and dec, partly because they're moving relative to each other, although not really quickly enough to notice in a human lifetime in most cases, but also partly because the Earth is precessing or wobbling over hundreds, thousands of years. And that wobble takes the equatorial coordinate system with it. But even that's really too slow to notice in a human lifetime. So what does the equatorial coordinate system have to do with equatorial mounts? Well, let's take a look at one. You'll see it has two axes of rotation, but instead of being flat to the ground and perpendicular to it, they're both at angles to the ground, and they're at right angles to each other. One axis, this one, is called the RA axis, and it's driven by the RA motor. This one is called the declination axis, and it's driven by the declination motor. And then you can use a go-to controller to slew across either the declination or the right ascension. Now, not all motorized EQ mounts have go-to controllers, and this is an example of one that doesn't. And this setup is called a clock drive, and it's very simple. The declination axis doesn't even have a motor at all. The RA axis has a motor that you see exposed here. This is just a simple stepper motor, and it's turning this gearing system very, very slowly. But it is rotating the RA axis at the speed that the Earth turns. Now, this setup has no computers, no go-to controller, and it's actually pretty hard to use for astrophotography. Now, regardless of the kind of German equatorial mount you get, the RA axis is going to have to be parallel to, and for the case of astrophotography, match precisely the rotation axis of the Earth. So if you're at 40 degrees north latitude, then the RA axis angle needs to be at 40 degrees to the ground. If you're at the North Pole or the South Pole, it'd be pointed straight up. And if you're at the equator, it'd be flat to the ground. Now, just so you know, not many German equatorial mounts can be made to sit flat to the ground. So if you live anywhere near the equator, make sure any German equatorial mount you're looking at will work at your latitude. Now you can see the declination axis has counterweights on it, and these are here to exactly match, or near exactly match, the weight of the telescope. So if you have them at the right weight and the right position, you should be able to move it just like this. So why does this work? Remember, with the AltAs mount, objects in the sky rotated as the telescope tracked them. Now let's look at the point of view of the telescope in an EQ mount. It looks at the horizon at an angle matching your latitude. You can see Horizon rising with his pelt directly to the right, passing over you, still with it pointing right, and then setting, pointing right. It doesn't rotate at all. The mount is flipping the telescope over. Now, those of you already familiar with EQ mounts probably know I'm being a little misleading here, because EQ mounts can't actually track an object from where it rises in the east all the way to where it sets in the west. And that's because they have to do what's called the meridian flip. Now remember, the meridian is an imaginary line that chops the sky into east and west halves. And German EQ mounts just aren't designed to go from the east past the meridian. And you can kind of see why. The counterweight bar goes higher than the telescope, which, well, it's kind of awkward, maybe not too bad. But now you're in danger of the telescope hitting its own tripod, which is bad. And so, you have to have a Cassegrain, which is usually a lot shorter. It's usually less of a problem, but really, you're not going to find a equatorial mount that will track past the meridian.
Some can be configured to go a little bit past, maybe 10 or 20 degrees, but never very much past. So what is the meridian flip? Well, once your telescope tracks an object from the east to the meridian, it'll stop tracking. And at that point, you need to wait for your object to definitely cross the meridian. Select it again in your go-to controller, and your mount will flip the RA and deck axes around 180 degrees, back to roughly the same position as before the flip, and then it'll keep tracking the object through the western sky. If you have a laptop with the right software controlling your mount, then it may do the whole process automatically, track the object to the meridian, automatically do the meridian flip, and then continue tracking the object through the western sky. It just depends on your software. Now there's one more kind of telescope mount that we need to talk about, and that's the Dobsonian, or Dob, just because they're really, really common. And that's because they're really simple. Now, a lot of people think of this as a kind of telescope, but really it's a Newtonian telescope in a Dobsonian mount. And even some retailers have them, like Orion telescopes. So let's take a look at one of theirs. And you can see it's a Newtonian telescope. There's the focuser. And it's in this mount. And the nice thing about these is you can get a lot of telescope for the money. Dobsonians are a kind of AltAs mount. So that, combined with the fact that very few of them are motorized, these are great for visual astronomy, not so great for astrophotography. So we end up with the best mount to use for backyard astrophotography is the German Equatorial mount with go-to controller. So let's take a look at some. And I'll start with one of the most common ones that people have bought, the Celestron CG5 GT. And here it is. This is the active part of the mount with the counterweight bar here. And here's the go-to controller and, of course, the tripod. Now, this CG5 is $750 retail US, but I've never seen it for more than $700 at any retailer. Now let's take a look at the specs. It has an object database so that you can just enter something like Andromeda Galaxy, and as long as you've aligned everything, the telescope will slew right to point right at those things. So that's really handy. It has a serial communications port that lets you connect it to a laptop and have your laptop slew it to different locations. That's something I've never done, but a lot of people do it and it can be really handy. And it has something that you should really look for, and that is this autoguider port. Now, this is an autoguider camera. It's basically a fancy webcam right there. But not only does it have a USB port to connect to your laptop, it also has this other port that connects directly to your telescope's mount, as long as it has an autoguider port. And how this works, and I'm not really going to get into this until the next astrophotography video, but it lets your laptop monitor the stars that this is looking at. And that way it can detect if your telescope's mount is moving a little too quickly or a little too slowly. And then through this port, this will tell your mount to speed up or slow down. And this can really increase the exposure time that you can get without getting star trails. So, really important feature to look for. And another thing to look for with any telescope mount that you're getting is the maximum weight or maximum payload that it can take. And that's listed on this table on Celestron's site. And you can see Advanced GT or CG5 has a maximum payload of 35 pounds. Now, that does not count the counterweights. One problem with the CG5 is I hear that is really optimistic, and a more realistic maximum weight is more like 20 pounds, or about 14 kilos. If you're using a Cassegrain, maybe around an 8-inch Cassegrain, you're probably perfectly fine with this, or a smallish refractor. Newtonians tend to be pretty bulky and heavy, so you may really be pushing things with a Newtonian on this mount. Now, the high end of the mounts we'll look at is the Orion Atlas EQG. Now, you can see the price is quite a bit more than the CG5 at $1,500 US. And you can probably also tell just by looking at it how much more substantial it is. And if we look at some of the specs, you can see it has a 40-pound payload, or about 18 kilos. So it will easily handle a pretty decent sized Newtonian, and certainly a nice big Cassegrain.
Has this nice celestial object database, auto guider, important to have, serial connection, and it also has a feature called PEC. Now that stands for Periodic Error Correction. Really interesting feature. I would say it's not a requirement, but something definitely to look for. And the reason it's there is because, your every mount is controlled by gears. And these gears aren't cut to enough precision for astrophotography just because it's not very practical. And even if they could, the wear would quickly make it not that precise anymore. So you just have to accept that every mount will move your telescope a little bit irregularly with enough imprecision that it will affect your astrophotography. What periodic error correction does is your mount records its own inaccuracies and then can play them back so that if there's a certain point where the gearing doesn't move your telescope quickly enough, it will speed up the motor just in that part by just the right amount to compensate for it. The last mount I'll talk about is the one that I have. It's the Celestron Advanced VX. It has a maximum payload of about 30 pounds. My Newtonian weighs 26 pounds, so it's kind of riding the ragged edge there, but it's handled it just fine. Now it does have an auto guider port, right there. This other port is a hand controller port that it comes with, of course, for your go-to controller. And it has another couple ports for things like controlling it from a laptop or for a separate optional GPS. And one thing to also look for is something I mentioned in part 1 with the dovetail that connects to the rings of your telescope. Here's the other end of it on your mount. And here's my rings and dovetail. And as I mentioned in that video, this is like a giant Arca Swiss head. And you just clamp it in like that, and you get a very solid connection between your telescope and your mount. This costs $800 US, a little bit more than the CG5. So now you have your OTA and your mount. How do you use it? First, level the top of the tripod. You can use a bubble level or a phone app, which is what I use. It's good to be on solid ground. The amount of weight you're going to put on it can make it sink into soft ground. Now I'll put the mount on it pointed roughly to geographic north, or geographic south if I was in the southern hemisphere. This is just a rough alignment that I'll correct later. Now mount the scope and get it balanced. Especially with Newtonians, balance depends on how the scope is oriented. So I usually balance it when it's roughly pointing at what I plan to shoot. Cassegrains and refractors aren't as affected by this, though they still are to some extent. Your camera adds a lot of weight to this, so we have to attach that before we balance. So how do you attach your camera? So my Newtonian has a moonlight focuser, a 2-inch focuser, and focusers come in both 1 1/4 inch and 2-inch kinds. This 2-inch focuser, I have the 1 1/4 inch adapter installed right now. Now to mount your DSLR, you need what's called a T-ring. Now T-rings have a bayonet on one side, specific to your camera manufacturer, and a thread on the other. So you just mount that in like that, and then you also need a T adapter, which has the same thread on this side and a 1 1/4 inch adapter on the other. So you screw that in, mount it in your focuser, and that's it. A better alternative if you have a 2-inch focuser is to use one of these. It's called a prime focus adapter. Again, it has a bayonet specific to your camera manufacturer on one end, but just a 2-inch cylinder on the other. And you just mount this on your DSLR and then put it into your focuser. Like that. Now, regardless of the kind of telescope you have, your camera is going to be spending quite a bit of time hanging down from its focuser. So your focuser has got to be able to hang onto your camera. Now, not all focusers can, and that includes the focuser that came with this telescope. So I swapped it out for what's called a Crayford focuser made by Moonlight. Now, Crayford focusers are pretty common on mid to upper end telescopes, and they use friction to move the draw tube up and down really smoothly. Now, if you can also get one with a dual rate focuser, where you have one knob that does coarse focusing and another knob to do fine focusing, then your job focusing will be a lot easier. I also specifically got a model with a shaft lock. Now, most focusers have a draw tube lock, where the locking mechanism pushes on the side of the draw tube, which isn't great because after you finally lock down your focusing, you lock the draw tube, it pushes on the side of the draw tube, which changes the focus slightly. By getting a shaft lock, you can avoid that problem completely because it only pushes on the side of the shaft, and it doesn't affect focus when you lock it. But in the end, the important part is that you trust that your focuser will hang on to your camera. You have to have so much confidence that you should be able to do this. And not worry about it falling off. As you're balancing your telescope, orient the camera so that as the RA changes, objects move horizontally across the sensor. Now, I just do this roughly for now, but I'll fine-tune it once I start observing. Astronomers with EQ mounts typically use what's called east-heavy balancing. And that's where, as your RA axis is here, if your telescope is on the east side of your mount, then that side is slightly heavier. And to do that, you can move the counterweight in. And then you can see it's biased slightly towards that side. This is a little bit exaggerated. But if you're observing the other side of the sky, and your counterweights are in the east and your telescope's on the west, then you'd move the counterweight out. And that way, it's, again, weighted slightly to the east. This is exaggerated, but so you get the idea of how that works. Now, why do we do this? Well, let's take a look at our gear toy again. Imagine this small gear is the one that's powered by the motor, and it's driving this big driven gear that's connected to the telescope itself. Now, if your telescope is perfectly balanced, then what can happen is as your driving gear, the powered gear, is pushing on the cogs of the driven gear, the telescope may shift a little, and then it'll start going faster than the motor's pushing it. And because of the little play in the gears, that'll make your stars jolt a little bit. But eventually the motor may catch up and then start pushing on it again, and then start pulling on it as the weight shifts around, and then you just end up with your stars making a zigzag pattern across the sky. By using east-heavy balancing, there's always tension on this driven gear, and that way your driving gear is always pushing on the cogs of the driven gear, and you don't end up with that problem. Okay, now the mount is pointed roughly north with roughly the right altitude, and the camera's oriented so that objects move horizontally across its sensor roughly when the RA changes. Now, nothing here is aligned precisely because I need the stars for that. And so I'll use the stars to gradually align each thing until it's precise. Now, this and other mounts have a sort of a shortcut method built in, which is great for visual astronomy, not so good for astrophotography. So instead, I'm going to use a method called drift alignment, which is the most accurate polar alignment method that there is because it uses the rotation of the Earth itself as a guide. Now, there's a lot of variations on this. I use one called DARV, which stands for Drift Alignment by Robert Weiss, who published this method to the Cloudy Nights website. Now, to use it, you need a go-to controller, digital camera, which obviously you're going to have for astrophotography, and a laptop. Now I have my camera connected to my laptop over USB. Laptop's running Windows. Now, this is actually a Mac, but truth be known, there's not a lot of scientific software for Mac. So us Mac users have to do something like run VMware or Parallels or Boot Camp or something. Might even be worth picking up a cheap Windows laptop from somewhere. The software I'm running is called Backyard EOS. It's a software package, costs $30, really reasonable. It's designed specifically for astrophotography. The other thing it's designed for, if you notice the name Backyard EOS, is it's made for Canon cameras only. Now, there are software packages to control Nikon cameras from a laptop, and none of them are designed for astrophotography the way Backyard EOS is. So it's at the point where the most common recommendation I've heard for Nikon shooters is to pick up a refurbished or used Canon DSLR body from eBay or something. You don't need a lens, just the body. So first, power up your mount. Now, to supply power, there's different ways, but since my mount came with a 12-volt cigarette lighter jack, I use a jump starter that has a 12-volt port on it. Now, someone at my astronomy club, hi Roland, if you're watching, said that this is not actually the best way to go because these batteries tend to die after maybe a year or something. And I've had this for quite a bit less than a year, so we'll see. He recommends instead using something that can withstand deep cycles. So it may be a marine battery or a UPS battery. Might serve you for a lot longer and be cheaper in the long run. I'm going to set quick align mode, which makes it work like a mount with just a clock drive. This sets the RA motor to run at normal Earth rotation speed. Now first, we need to get our focus, and Backyard EOS is really going to help with that. But let's first point at a reasonably bright star, maybe magnitude 1 or 2, somewhere in that range. And I got one right here. Now have Backyard EOS get a live view from your camera, and you can see an out of focus star there. And so now we need to get it right in the middle, or as close to the middle as we can, of the crosshairs. Just using the slewing functions on the telescope. Okay, now look at that number that says 11.6, 11.7. That's called the FWHM, or full width half medium number. There's a formula to generate that, and it's worth looking into, but I'm not going to go into that right now. But what you need to do is change your telescope's focus until that number is as small as possible. And that's what I'll do right now. So 7.3, 7.2, 6.8, 5.8, so it's getting better. Now it's going up again, so I'll push back the focus, and now I'd say we're in focus. Now that you've got good focus, it's time to orient your camera so that when you slew the RA motor, objects go pretty precisely horizontally across your camera's sensor. The target lines of Backyard EOS help you get this really precisely. So you can see the stars going up and to the right, or down and to the left. So I need to rotate the camera a little. You can also rotate the OTA, but you may shift its balance if you try this. And now, my camera is aligned very precisely. Now that's two things that we have precise now. First, the focus, and then the alignment of the camera. Now let's get into polar aligning your mount. And let's start with making sure the azimuth of your mount is correct. Now, this is an EQ mount. Aren't we done talking about azimuth? No, we're not, because we're talking about actually moving the mount to get it aligned to the celestial pole. And in that case, we have to adjust the mount's azimuth and its altitude so that it can move the telescope properly. So let's start by aligning your mount's azimuth.
If you're in the northern hemisphere, point your scope at a star near the meridian and towards the south. Those in the southern hemisphere choose a meridian star towards the north. Now, slew your mount so that the star is on the right side of the screen, near the horizontal crosshair. This is the east side of your field of view if you're in the northern hemisphere. Now set your mount's slewing speed to be just slightly faster than its natural tracking speed, For Celestron, that's motor speed 3. Now I'll use the snapshot feature of Backyard EOS. Set the ISO to something fairly low depending on how bright your star is. I often set ISO 100. Set the duration to 125 seconds. Now get your go-to controller ready and be ready to slew it west in the northern hemisphere or east in the southern. Start the snapshot and hold your telescope in place for 5 seconds to burn the image of the star in. Now at 5 seconds, slew your telescope west for 60 seconds. Once you get to the 65-second mark, immediately slew your telescope east again. Let go once the exposure is done. Now take a look at the image that comes back. You can see it has a long, less than shape with a bright spot at one end. That bright spot is where you held the mount in place for 5 seconds, and it tells you where the star started. If the line moves up during those 2 minutes, like it is here, then your mount's pointing too far to the west of the north celestial pole. So adjust your mount's azimuth in the right direction and try again. As you do this many times, you'll get a feel for how much to adjust your mount based on how wide the less than shape is. Now do the same test again, and again, until you see the star after the U-turn track right back across its path before the U-turn. It can't be off by even a little. It has to track back across its own path precisely. Now you have the azimuth of the mount pointing directly at the north, or at your celestial pole. Or at least seeming to, and I'll get into that after the next step. And the next step is to get the altitude of the mount pointing at the celestial pole. For this, point at a similarly bright star near the western or eastern horizon. Now do the same test again, this time adjusting your mount's altitude until the star tracks east, right on top of where it tracked west. Make note of which way you have to turn your altitude adjustment to correct the mount, so you don't have to think about it each time. Okay, now your mount is pointing precisely at the celestial pole. Or maybe not. Go back and repeat the test for the azimuth, because in changing your altitude, you may find your azimuth needs a little correcting. Well, now you have precise focus and precise polar alignment. Now's the time to turn the mount off, because you need to start the process of telling the mount which way your telescope is pointing. And every mount with a go-to controller has a procedure for doing that its manual describes. And I'm going to use a procedure called two-star alignment. First, put the telescope in its home position, which points it at the celestial pole. Most mounts will have little marks to show where that is. Then, start your mount's alignment procedure. With this mount, you first get a rough alignment. Then I use Backyard EOS to point the scope very precisely at the first alignment star. Once that's done, I do the same procedure for the next alignment star. Well, now your mount has precise polar alignment and the go-to function is aligned. Now I've used the go-to controller to tell it to point to the beehive cluster, which is Messier 44. The camera's open, but I can't really see anything, so I'm going to use this HD function to increase the gain. And now I can see this sort of house shape, which is what really distinguishes the beehive cluster. So now I'm going to take a 10-second exposure snapshot at maximum ISO, which on this camera is 1600. And I'll just want to take a quick check to see how things look. Okay, that's our cluster. What I'm going to do now is close the shutter and then start an imaging plan. So I'm going to enter the target name, which is M44. I'm going to set a mirror lock delay at 5 seconds. That gives the mirror time to settle down. I'll use ISO 400 and a duration of 30 seconds. Bulb mode, and that should do it. So let's see how we do on our polar alignment. I'm going to press Start Capture. Our shutter open. Now it's waiting 5 seconds to let the telescope settle down. And now it's starting to image. And that's 30 seconds done. It's going to download the image to the computer and we can take a look.
And there we go. Actually, we're zoomed in. Let's zoom out a bit. There's the house shape. And let's see how good polar alignment was. And over 30 seconds, it moved a little bit, but not too bad. I think I can deal with that. Let's see how we do at 1 minute. So 60 seconds. Okay. Now let's wait for it to download the image and see how it was over 1 minute. And we can see it's not great alignment. I'd have to work on this a little more. Well, I hope that gave you everything you need to be a really good consumer on telescope mounts. And combined with part 1 I did on telescope OTAs, you should be able to put together a really great astrophotography rig with no regrets. In part 3, I'm going to talk about autoguiders, and those will really increase the number of objects that you can image. But you do have to make sure that your mount can handle one. And I'll also be talking about what's probably the most mysterious part of this whole process, and that's image processing. So thanks for watching, and thank you so much for subscribing. And I will see you next time.